Morning, guys. This is your Vesper theory lecture. All right, so this weird movie from 2017, The Shape of Water, where this the amphibian man and this woman, they fall in love and all that. Well, that was a weird movie, not gonna lie. But so the shape of water, the molecular shape of water, is what we're really focused on when we talk about the shapes of these molecules come for pre-AP Chem. Um, it's not really touched in general chem too much, but in pre-AP, I want to cover this because this actually is something that you're kind of expected to know and recognize when you come into AP, if and when you go into AP Chemistry as a senior. So what is Vesper theory? So just be mindful that electrons, what they tend to do, because they're the same charge, what they're going to want to do is they're going to want to repel from each other. And so if you have two bonds, remember that bonds are consisted of electrons, what they're going to want to do is they're going to want to get as far from each other as possible because they have the same charge. Lone pairs of electrons, and a bonded pair of electrons, what they're going to want to do. So remember, these are just, if you remember from the structure before, you saw this here. So this is a lone pair, and this is a bonded pair over here. So because they are the same charge, electrons, negative, they're going to want to also push away from each other as far as possible. That pushing away, that repelling, that's what's going to create the shapes you're going to see in a bit. So the valence shell electron pair repulsion theory, or Vesper theory, it helps predict the shapes of molecules based on the idea that you have your electrons on a central atom and they want to get away from each other as far as possible. So you have a key word to be mindful of is electron domains. So electron domains, it refers to an area of high electron density. It can either be a bond or a lone pair. So let's say you have this element X and you have this bond and this, something like this. So here you have 3 domains on that central atom. You can also have, let's say, if this is another element, random element, you have 1, 2, 3, 4. Well, there are 4 domains because you can count 1, 2, 3, 4. But if you saw, say, a double bond instead, even though this is a double bond here, this is still considered 3 electron areas around that central atom. So this is also 3. Similarly, if you had, let's say, X here, and you have a triple bond and then a single bond, this is 1 electron area, this is another electron area, so this is going to be 2 domains. And that is something to be mindful of when we're doing this section of the unit. So below the table, I want you to write out this part where it talks about the number of domains, and we're looking at the electron geometry. So the electron geometry is the number of domains, number of electron areas around a particular central atom that we're focused on. So if there are 2 electron domains, it's a linear geometry. So it'll be something like this. So 2 domains, it's linear. If you have 3 domains, so let's say this is X, it is trigonal planar. If you have 4 domains, it's going to look something like this. It's kind of weird. So it's like this, and then here, and then here. It's kind of crazy, but the idea is that this part is here, and this is coming towards you, and this is going away from you. So that is 4 domains, whatever those electron areas are. Just so you know that for the electron geometry, you're going to have certain degrees associated with them. So if you have a linear, so you have 2 domains, it's 180 degrees. So it's kind of like what you see here. If it's 3 domains, it's 120 degrees. And then if it's tetrahedral, excuse me, or 4 domains, it's 109.5 degrees. So you'll notice that regardless of what those things are, whatever is attached, however many domains you have, that's a set degree. Remember, if you're thinking about it, if it's a circle, 180 plus 180 is 360. 120 times 3 is 360 as well. If I said 160 earlier, I apologize. But you'll notice now that the molecular shapes are slightly different. Notice how it changes based on what is attached to it. This is the molecular geometry. That's what we're looking at now. The previous slide was electron geometry. This is now the molecular geometry. The molecular geometry, that's what depends on what you have, what specifically is attached to the central atom. The first one, domains don't matter. It doesn't matter what it is. However, with the molecular geometry, it does. And that's where you get other shapes and different angles as well. So molecular geometry, if it's 2 bonds attached to a central atom, it's still linear, 180 degrees. Notice, however, with this pyramidal right here, you have 4 domains attached. 4 domains. So the electron geometry would be tetrahedral. Yeah. But if you have 3 bonds and 1 lone pair, the molecular shape is a pyramidal. And notice the angle is less compared to the tetrahedral. In the bent one, this is a bent shape. There's still 4 domains, so its electron geometry is tetrahedral. However, the number, notice how it's because it's 2 lone pairs and 2 bonds, the shape is bent because you're looking at that shape, and notice how the angle is way lesser compared to the other ones. So why is that? Well, if you notice, what this kind of tells you, so you can all kind of figure out, is that a lone pair, like here, here, and here, they have a greater repulsion, meaning that a bond is going to be, if you have a bond up here, let's say this one, versus this lone pair here, the lone pair is going to cause a greater repulsion and push the other atoms that are bonded away from that lone pair. With this one here, with the bent, with the 2 lone pairs, they're pushing these two electron domains even more away from the 2 lone pairs. So you have this right here, H2CO, and that's formaldehyde. So you see that you have 3 domains attached to it, and they're all bonding, meaning that they're all, so this is a domain, that's a domain, that's a domain. So 3 domains, they're all bonds, there's no non-bonding, no lone pairs. So the electron geometry is trigonal planar, and the molecular geometry is trigonal planar as well. So it's still the same. Here you have CS2. On this carbon, you have 2 bonds right here and here. So all you're focused on is just the central atom. So there are 2 non-bonding, sorry, there's 2 bonding and 0 non-bonding, no lone pairs. So that means that the electron geometry and molecular geometry are both going to be considered linear. CH4. So this is methane or carbon tetrahydride, or all of us, we all know how to name things, right? Hopefully. So there's 4 domains. So we know if it's 4 domains, regardless what it is, it's always going to be a tetrahedral electron geometry. And because they're all bonding, they're all considered the molecular geometry is also tetrahedral as well, or molecular shape, I'm sorry. So you have NH3, ammonia, nitrogen trihydride, whatever. 4 domains, but now notice how there are 3 bonds and 1 lone pair. So I'll pause for a second. You should know the electron geometry is tetrahedral. However, there are 4 domains, but only 3 of them are actual bonds and one's a non-bonding one. So that means my shape is now technically trigonal pyramidal. Here's H2O. You have 4 domains, 2 bonding, 2 non-bonding. So 1, 2, 1, 2. This shape right here, this is going to be bent, but the electron geometry is still tetrahedral. CO2, so you have your carbon in the middle, domain here, domain here. They're both bonding, doesn't really matter. It's going to be linear for both the electron geometry and the molecular geometry.